Today's lesson is on metal reactivity, and you'll find it in Chapter 2, Section B of your comm textbook. We're going to discuss what metal reactivity is. We're going to describe the behavior of reactive and non-reactive metals, and how we can tell if a reaction will occur when two metals come in contact with each other. We'll also understand why it's harder to purify some metals than others. Clearly, not all metals behave the same. Today, we took copper powder and we had to heat it to get it to react with oxygen to form a black powder called copper oxide. Other metals react spontaneously when exposed to oxygen. For example, magnesium can react without heating to form a black, almost tarnish-like substance, similar to that which you may find on your good silverware that your mom might ask you to clean during holiday seasons. If we were to take that magnesium and heat it in the presence of oxygen, we actually see an explosion. And this was used to help develop photography. The old flash bulbs were actually formed from magnesium inside a little container. Magnesium is also used in fireworks. So where copper had to be heated to react with oxygen, magnesium under the same conditions causes a violent explosion. Now on the other end of the spectrum, on that non-reactive side, we can see that gold doesn't react with much of anything, which is also why it's useful to use gold for jewelry. You don't want it to tarnish when it touches your skin. We use it for leads in electronic devices so that we get good signals. The first slide in this lesson showed these metals reacting with water, and you don't really think of a metal as having a violent reaction with water, but indeed there are certain metals that are so reactive they explode when they come in contact with water, and in order to ship them they have to be shipped in an inert oil to prevent unwanted explosions from occurring during shipping. So this behavior of very reactive to not so reactive has been summarized by scientists into something called an activity series, and it's very useful for us to predict what will happen when different metals come in contact with each other, and what kind of care we need to use when handling and storing certain metals. This is the activity series shown in your textbook. It lists the elements from most reactive, back to we saw the lithium exploding in our opening slide, to the least reactive, our gold down here on the bottom. The more active metals are harder to purify. Some vocabulary words that you may have seen from your Quizlet activity: electrometallurgy, pyrometallurgy, are ways in which we can purify metals. Electrometallurgy requires the most energy as we have to pass electric current through these metals. And the reason for this is metals like lithium and potassium are so reactive, they're going to bind onto anything that's near them. So we really have to put a lot of energy in the system to get them to let go and to become elemental and existing only as lithium atoms. A more active metal is going to cause the ions of a less active metal to revert to its elemental form. And you're probably asking, what the heck am I talking about here? In the next slide, I'll give you a little example. But a good analogy is to think of metals as bullies. If lithium, a very strong and bully element, comes in contact with an element that's not quite as strong, for example, lead, lithium wanting to bond with something is going to get rid of the element that lead is connected to. And in a moment, hopefully that'll seem a little more clear to you. So I call this the switcheroo. Think about a couple going to a prom, and there's a big bully who shows up who doesn't have a date, and he tells the wimpy guy to go get lost, and the bully guy ends up with the girlfriend. This is what's going on when metals come in contact with each other in an aqueous system. And we can see here we have two test tubes, and in one test tube there's an iron nail and a solution of copper sulfate. So in the solution we have copper ions and we have elemental iron. So what's going to happen here is iron is more active. Iron is the bully. Iron is going to tell copper, you go away from the girl, you go sit by yourself, and I want the date. So when we come back, what we find, indeed, is copper wire. So copper is now elemental, and iron gets the girl. So we can see that iron has the girl, and copper is by himself. So the more active metal will take the place of a less active metal when they're in an aqueous solution. So we can use that activity chart to see when I bring certain combinations of chemicals together, what's going to happen? Will there be a reaction or not? Now, let's say a less active metal were in the copper sulfate solution. We would then see no reaction because the wimpy metal isn't going to be able to make copper let go of its anion or its partner to form a new compound. Now, if this seems a little confusing to you, relax. We're going to practice doing metal reactivity reactions in our lab tomorrow. But the summary here is that more active metals are going to be very difficult to find in their pure elemental form in nature. So you're not going to walk down the street and find a nugget of zinc. But you might find a nugget of gold or copper or other metals that are fairly unreactive. You will need to put more energy into those reactive metals to purify them. So it's going to take a lot of energy to purify lithium or sodium. A more reactive metal will also push a less reactive metal out of a compound when it's in aqueous environment. And it's these reactions that we're going to practice tomorrow in our lab.